Hello, my name is Sai Rovella, and today I want to talk to you about our work in determining coastal flood risk in Bangladesh as part of the Climate Grand Challenges projects. Bangladesh is a coastal, low-lying delta whose exposure and vulnerability to multiple hazards in the face of climate change make this an important area of study. We are focused in the southwest part of Bangladesh, although our interest is all over Bangladesh, but our present focus is in the southwest of Bangladesh. As I zoom in to this southwest region, in particular, a part of the southwest shown by this beige colored region is of our interest. To the south of this region are Sundarbans, and further up north are dotted numerous polders, which you see here in white, showing the embankments that enclose the population within. In the southwest area, particularly where we're interested in, these polders have been playing an enormous role in managing the lives and livelihoods of population that live within them. Unfortunately, while they have been around for a long time, so have complications that have emerged due to their existence and use. And this intersection with the hazard is worth a study. For example, the embankments in many cases, and let me just go over these polders here. So polder number 15 is where my cursor is, next to 14-1, slightly further to its east. Further up is 14-2, and 7-1 is a bit north of 15, where Koira is, and 7-2 and polder 4 and polder 5 and polder 10-12. These are our primary study areas, and within them we're focused on a few regions. But why are we interested in these polders and their interaction with flood risk? Well, although these polders are meant to protect the population within, many of them are in a state of disrepair. So when Cyclone Isla hit Koira, what happened was that the embankment was breached. It didn't overtop. The storm surge from the ocean, because that Isla brought in, didn't really overtop the polders embankments, but it breached them. And it deposited a huge amount of salt water that stayed there for years thereafter, completely destroying a source of livelihood. In fact, in many of these polders, there's a transition that has happened from agriculture to aquaculture. And now people actually breach the polders to bring salt water in to run their shrimp farms. There are other complications. The land within the polders is subsiding. So it is easier for flood related issues to amplify. In fact, because of the way construction of these folders, the tidal waters that come in, the storm tides, for example, ride much further north, because instead of otherwise just inundating the land, these polders are protected. So the tidal amplification causes this water to go much further north, depositing a great amount of salt or the salinity further up north than it would otherwise have. So not only is the salinity an issue here, but it's also an issue much further north. And the sluice gates, which were to be used to properly manage these polders, um, for various reasons of mismanagement, in part, um, have silt deposited on the riverside. They're just not operable anymore. Looking at sedimentation processes, the changing river morphology and the morphodynamics are not only interesting in their own right, but they're abutting against these embankments, causing huge stresses, which would then feed back to a breach a little bit further down the road. Were these polders a good idea to begin with? Could there have been alternatives, such as the ineffective use of the Sundarbans, a nature-based solution, perhaps, and a proper management of fresh and saltwater, seawater flooding? that would have that have led to perhaps a better or more sustainable state? These are the types of questions we're interested in answering, particularly at the intersection of infrastructure and the hazard. In particular, in our case, cyclone-induced risk, including winds. We are interested, for example, in shelters. Um, and now shelters that we've been studying have require uh, to take on multiple perils, including winds as well as flooding. And their job, although Bangladesh has done a great job, an enormously great job in protecting lives, the transition now is to help them protect livelihoods. So, considering um, all these um, infrastructure related issues, the exposure of the population in the region, and the vulnerability that exists, it becomes very important for us to study the compound risk. And by compound risk, we mean the coastal, fluviotidal, and inland inundation. As a consequence, we've been focusing on three areas which are shown here in black. The bottom here are Munshiganj and Ishwaripur. In the middle are Ashashuni and Borodal, and further up north is Keshapur, each having slightly different issues. Coastal issues and coastal flooding dominate uh, Munshiganj and Ishwaripur. Riverine issues, salinity related issues dominate um, Ashashuni and Borodal, especially because, as I mentioned, these arrangement or geometry of these polders brings in actually much more salt water than would otherwise. And further up north is Keshapur, which has a different kind of flooding issue. In Keshapur, fresh water from rain comes and it waterlogs, and it just waterlogs, and the land is essentially unusable for months. And it doesn't drain, and it can't be pumped out because, in part, the water level has been rising, partly because um, there's been so much sedimentation that the riverbed is rising. And there's numerous complications because of this that need to be considered. So our job is to ask ourselves, well, how do we determine uh, the compound risk in Bangladesh from coastal, fluvial, and inland components, considering both tropical cyclone induced flooding, as well as extreme rainfall, seasonal extreme rainfall, and erratic rainfall, and other issues related flooding. And our interest is in building such an integrated flood model, coupling all of these different components, and study its interaction with salinity, study its interaction with morphodynamics, study its interaction with infrastructure. Our project just got started, and right now we are focused on the coastal component, and we will steadily build in these other components as we go. For the coastal part, we started by building out an ad-circ mesh, a finite element mesh, as you can see here, and we've only built the mesh as far as the coastline, about 2 meter water height and water depth. And further, we will grow this mesh and we'll integrate it with other models, including Sphinx, for example, as well as uh, uh, other models such as HECRAS and HMS as needed. But right now we're focused on the coast. And we built this ad-circ mesh. It's at least a kilometer resolution, and we can easily bring it down to 200 meters. The mesh extends much further south, and it extends down south, as I will show you here, to the Indian Ocean, where it starts off with an open boundary condition. And then it comes back to our region of interest. And I'm just going to focus a little bit more now in this area to be able to discuss some of the things we've done. So shown here in red is Sidr, the cyclone track for Sidr that is going through Bangladesh. And we were able to calculate the maximum elevations for Sidr as a validation. And our validation results at Kepupara and Heron Point, where tidal gauges are available, show that we are not only able to track, of course, the tides, but also the storm tides. And this was quite satisfying. for us to have built. And as a result, we were able to undertake climate risk assessments. And that process begins with simulating number of tropical cyclones. Here the tracks are shown passing through Bangladesh. And this downscaling technique, which is based using a physically based downscaling approach, using statistics only to seed and draw out the initial seeds of tropical cyclones, is a rather remarkable technique that has been applied in many, many places around the world. And these synthetic storms, where there are abundant observations, appear to match, the wind distributions appear to match rather well. But nature hasn't yet produced enough storms for the purpose of risk assessment. The tails are really not well resolved, and obviously the number of storms produced in a future scenario is exactly zero. So we use the synthetic downscaling technique to produce storms of downscale from different climate models under different scenarios. And we produce thousands of tracks in present climate and future climate for reanalysis and climate models. And through suitable procedures, start to gather information from them. Well, one of the things that we can do is not just do, you know, large scale studies, but we can also do local studies. For example, here in Shamnagar, you see the wind exceedance probability for one particular model, the CAN-ESM model, that is comparing in blue the current climate versus in red an SSP5 8.5 scenario. Now, we can of course do this at many different places. Here we see Nashashuni in Keshapur and so on and so forth. So all of these locations we are able to then assess these wind distributions. Of course, we can bring this wind distributions to near surface winds and use that to quantify the wind hazard, both locally as well as through a whole region. So having shown you something about quantifying wind risk, we will now turn to storm surges. From the downscale tropical cyclones, we can run them through the AdCirc model and simulate storm surges. As you see here for tropical cyclone Sidr, we are showing you the maximum elevations, and this could be done for every synthetic track that we've generated. And we observe the storm surges at these locations that are shown in black circles. The locations in green diamonds, which I have some cursors over at Cox Bazar and Charchanga and Kepupara and Aron Point, actually have tidal gauges there. But in the other locations, these are just virtual stations where we just assess what the storm tide is. And the accompanying video, you can see an animation of the tropical cyclone Sidr, which shows you how the storm tide progresses. Now, once we are able to do all these simulations at these locations, we can start to assess risk. And what do we mean by that? For example, if I were to go at Heron Point and click here, we can see that there are three curves on the top, the x-axis being the return period, y-axis being the storm tide in meters, and the blue curve is what we have in current climate, the 58% quantile, and the magenta curve is for CMIP5 models. We have a total of 6 CMIP5 models and 7 CMIP6 models, and the composite assessment from all of these is shown in the magenta and red curves. And you can see that there is substantial amplification of risk. A 100-year return period has moved up, which also means that what was a 500-year return period is now less than a 100-year return period. Now, obviously, there are uncertainties associated with these calculations. And at the bottom, you see an example of the CMIP6 with its confidence interval overlapped with the confidence interval that is calculated for those models in present climate. Of course, these models have been calibrated to reanalysis. Now, this type of assessment we can provide for any point within a, of course, with a suitable radius of interest. For example, at this virtual point, Chen, we have a similar graph for the three periods, and in the bottom showing the uncertainties or the confidences really for CMIP6. Now, we can not only do this at a you know point by point at a local scale, but we can also do it on a regional scale. For example, in the southwest region, which is roughly going from station Alex to, I suppose, station Gabe, and these names are based on students that are in my lab because they're virtual. So, and students, and of course, my mentor, Kerry Emmanuel is here. And so, so we've named them that way. So we can, of course, aggregate the risk into regional risk. And here's the regional risk that we see the picture for Bangladesh in the southwest region, again, comparing present climate with CMIP5 and CMIP6 scenarios. To the degree that one must consider these scenarios and to the degree that these have to go into planning, we have the capability of informing this. Again, I want to emphasize that this is not possible simply by using observations in present climate and somehow trying to infer something about future climate. This is also the mechanism by which we would deal with non-stationarity. What exactly do we mean by non-stationarity? You know, if we talk about 1,000 or 10,000 year storm in present climate, it's a moot point because, I mean, the climate would already have changed. So if we are able to model the change in climate, for example, as a rolling time window over decadal or 20-year periods, and model risk, as in model these return periods as evolving over those windows, that gives us a handle on non-stationarity. Of course, the variances will grow as we go further out, or the conferences will become weaker as we go further out, but nonetheless, we have a basis using physics to be able to do this. And in present climate, that physics matches up with observations, which is an important point to consider. Even in present climate, as has been argued, even in present climate, if we need to resolve the very tails, once again, let me emphasize that nature hasn't produced enough storms for us to do that, which is good news perhaps, but it really hasn't. Um, and so we feel that this technique that starts with providing a catalog of tropical cyclones that are physically downscaled without using detailed simulations, and then coupling those with physical processes. The ADCIRC model that we have here is meant for climate risk. It's not meant for engineering assessments. So we could, for example, add resolution as we need it in locations where we need it. But at the scale that it is, where the coarsest resolution is or the order of 25 kilometers and the finest resolution of the order of 100 meters, but on average at the coast it's around a kilometer, is enough for us to assess what the risk is. And it's very rapid. We only need about 40 cores and about 10 seconds worth of simulation time to simulate a typical storm going through. So all these issues said and done, we feel we're in a very strong capabilities of doing not only coastal risk, but also are being investigating and are working and have the capability to study riverine processes as well as inland flooding.